Hello everybody and welcome to this A-level chemistry video about energetics. This is the second energetics video in our series and it will complete the energetics topic. In this video we will be looking at the calculations to do with enthalpy change experiments, where we're looking at Q equals mc delta T to work out the heat energy change, and then we'll look at how you work out the enthalpy change using that heat energy change and the number of moles. Then we'll explore the different types of experiment that there are. We'll focus on 3 types of experiment and we will look at some examples of each of these types. And then we will explore the concept of extrapolation using temperature change graphs. There's normally a graph drawing question on an A-level paper, and this is one of the most likely candidates that you'll encounter. There are a number of different types of enthalpy change experiments that we can do, but what they all have in common is the quantities that they need to measure. So remember that enthalpy change of a reaction is the heat energy given out or taken in as the reaction proceeds. And so we need to have an experiment that will measure the amount of energy that is produced or released. And usually this involves transferring the energy to water, but not necessarily always. And so to find out how much energy has been released or taken in, we need to measure 3 things. Firstly, we need to know the mass of a substance that is being heated up or cooling down. And in chemistry we give that the symbol M for mass, and most commonly the units for mass are in kilograms, but they might sometimes be in grams. We need to know the temperature change for this substance. Has it got hotter? Has it got colder? And the symbol for this is delta T. And so the delta means change and capital T stands for temperature. Now, because of the way the Kelvin scale works, this can either be in Kelvin, which is a capital K, or it can be in degrees C. And the reason for this is if our temperature begins at 20 degrees C, and the temperature increases to 25 degrees C, delta T is of course 5 degrees C. 20 degrees Celsius could also be written as 293 Kelvin, because to turn degrees Celsius into Kelvin we add 273. And so the temperature would go up to 298 Kelvin, because 25 add 273 is 298. And so whilst the numbers are different, the temperature change is the same number. And so what that means is a 5 degrees Celsius temperature rise is the same as a 5 Kelvin temperature rise. And the final quantity that we need to know or to measure is the specific heat capacity of the substance that is heating up or cooling down. And this has got the symbol of a little lowercase c. And the specific heat capacity of a substance is the amount of heat energy needed to raise 1 kilogram of that substance by 1 Kelvin or 1 degree C. Remember, those are the same thing. And so the units of specific heat capacity are kilojoules per kilogram per Kelvin. And so, for example, if we had 1 kilogram of a substance that had a specific heat capacity of 200 kilojoules per kilogram per Kelvin, and if this substance was at 20 degrees C already, and we wanted to raise its temperature to 21 degrees C, that specific heat capacity tells us that it would take 200 kilojoules to do that. If we want to raise it by a further 1 degree C up to 22, then that would require another 200 kilojoules of energy to do it. And so we can work out in proportion like that. Now, the ever such a slight complication here is that the units of specific heat capacity are kilojoules per kilogram per Kelvin, or they could be joules per gram per Kelvin as well. And if you think about it, that makes perfect sense, because if it would take 200 kilojoules, that means 200,000 joules, to raise the temperature of 1 kilogram of this substance by 1 Kelvin, remember a kilogram is 1,000 grams, what we're saying is 200 kilojoules per kilogram per Kelvin is the equivalent of 200,000 joules per 1,000 grams per Kelvin. And so if we get rid of all 3 of those zeros from both of those digits, we're left with 200 joules per gram per Kelvin. So in effect, if we go back over to the right hand side, we've divided the kilojoules by 1,000 and we've divided the kilograms by 1,000, and those effects cancel each other out. And so we can have either of these two as the units. And I would express a marginal preference for using the top one because it makes some of the later steps a little bit faster. Now this is normally given to you in an exam, so don't spend ages trying to commit this to memory, but the specific heat capacity of water is 4.18 kilojoules per kilogram per Kelvin. And so what that means is if we have 1 kilogram of water, it would take 4.18 kilojoules of energy to raise the temperature of that water by 1 degree C. But like I say, normally you'll be given this quantity in an exam question. And so those quantities can be linked together in this equation, where the heat energy change is equal to the mass of the substance multiplied by the specific heat capacity of that substance multiplied by that substance's temperature change. Or perhaps more simply, Q, that's the heat energy change, is equal to M, mass, times by C, specific heat capacity, times by delta T. So Q equals MC delta T. Now remember, what we've calculated here is Q, the heat energy change, as opposed to the enthalpy change, which will usually be the purpose of the experiment. And so what we need is one last calculation that links our heat energy change with enthalpy change. And the way to explore that is to think about what the units are for enthalpy change. And the units of enthalpy change are kilojoules per mole. And so in order to calculate the enthalpy change, we need to take the energy, which is in kilojoules, and divide it by the moles. Because when you take kilojoules and you divide it by moles, we get kilojoules per mole. And so once we have calculated our heat energy change, we need to divide the heat energy change by the numbers of moles that were involved in that particular experiment. And that might be, for a solid, moles equals mass divided by relative molecular mass. If we are working with solutions, we will be using the equation moles equals concentration of that solution multiplied by the volume of that solution in decimeters cubed. And that's how we'd calculate our moles value, which we would then plug in to the expression over here. And last of all in this, you need to remember that exothermic reactions have got a negative enthalpy change. And so you need to remember to put the negative symbol in for the delta H value for the exothermic reactions. And you'll recognise that, remember, because the temperature will have increased. And similarly, but in the opposite way, for an endothermic reaction, the temperature change will be a drop. And so the endothermic will have a positive enthalpy change. And so you can add that in at the very end of your calculation. A plus in front of your number if it is endothermic, a minus if it is exothermic. And so a calculation like this based on experimental data could be worth as many as 3 or 4 marks in an exam. Before we take a look at the experiments, I just wanted to clarify the difference between two terms that are often used to mean the same thing in daily conversation, but really in chemistry they're quite distinct and different, and I want you to see this clear difference. So heat, first of all, is a measure of the total energy of all the particles in a substance. And so heat is a type of energy. Temperature is a measure of the energy. It's related to the average kinetic energy of the particles in a system. And so this is to do with the fact that if particles have got more kinetic energy, they will move around faster, and the average kinetic energy of the particles will increase, and the temperature will increase, because temperature is how we experience the kinetic energy of the particles. We will experience something as hot, and the thermometer will register it as being hot because particles will collide with that thermometer with greater energy. You can have something that is a high temperature though, but has a low amount of heat energy. So if you consider a cup of coffee or tea that you've just made, the water from the kettle has boiled, so it's at 100 degrees Celsius, but the cup of coffee doesn't contain as many particles as some other situations. And so if you imagine a bath that might be about 40 degrees or something like that, maybe a bit more, but because there are significantly more particles in the bath will have a greater amount of heat energy, a greater amount of heat. And so we would say that the bath was at a lower temperature but had a greater amount of heat. But just to link it in with our GCSE physics, if we were to put the cup of coffee near to the bathtub, the heat would flow from the hot cup of coffee to the bath. And so it doesn't matter how much total heat there is in a system, the overall movement of heat energy is from higher temperature to lower temperature. Now there are actually 3 different types of experiment that you could be expected to work out the enthalpy changes with. And the first one that we're going to consider is the situation where you might have 2 solutions and you're going to add one to the other. And an example of this is a neutralization reaction. And so if we considered an experiment where we had 20 centimetres cubed of 1 mole per decimetre cubed concentration of hydrochloric acid and similar quantities and volumes of sodium hydroxide, but this time we've got a little bit more, a greater volume, and let's say that the starting temperature of both of these is 20 degrees C. What we would need to do in this experiment is we would need to take the contents of one of the containers, put it into the other, and then in this reaction, which would be exothermic, because neutralization is always exothermic, we would track the temperature rise. And so the temperature change, let's say the temperature went up to 35 degrees C. The temperature change is the temperature at the start, 20, subtracted from the temperature at the end, 35. And so delta T is 35, take away 20, which is 15.0 degrees C. So that's where we get our delta T from. C, the specific heat capacity, remember, we make an assumption here, which is that solutions have got the same specific heat capacity as water, in other words 4.18 kilojoules per kilogram. This is a reasonable assumption because most of a solution will be water. Even a 1 mole per decimetre cubed solution of sodium hydroxide will not have very many particles of sodium ions and hydroxide ions compared to the number of water molecules there are. So this is a decent assumption. And remember, the final quantity that we needed was M, which is the mass of the substance being heated. Now here is the first tricky point, really, because even if the thermometer is only in one beaker, for instance the right-hand beaker, the one that the liquid was being added to, the temperature is rising across both of the solutions mixed together. And so M in this instance will be the combined mass of both of the solutions. Which brings us to the next assumption, which is the density of a solution will be equal to the density of water, which, for the reasons we mentioned earlier, is a reasonable assumption. And the density of water is 1 gram per cubic centimetre, or 1 kilogram per cubic decimetre. And what this enables us to do is to say for the sodium hydroxide we had 30 centimetres cubed, well that would be 30 grams worth of liquid. And similarly for the hydrochloric acid this would be 20 grams worth of liquid, or more usefully I think 0.030 kilograms and 0.020 kilograms. And so since Q equals mc delta T, Q now for us here equal to 0.050 kilograms multiplied by 4.18 multiplied by 15, which gives us 3.135 kilojoules. Now the next step, remember, to work out delta H is to divide the energy change by the moles. And I strongly recommend you show your working out in a similar way to this. Moles of HCl is equal to concentration times by volume, which is equal to 1 for the concentration multiplied by the volume, which is 0.02 decimeters cubed because to convert centimetres cubed into decimeters cubed, we multiply by 1,000. And then this gives us 0.02 moles. For sodium hydroxide, moles again is 1 for the concentration times by the volume, 0.03 this time, which is going to equal 0.03 moles. And here comes the second complication. When you're working in a situation like this, we need to identify the chemical that is in excess, which is the sodium hydroxide, and the moles of the chemical that is limiting, which is HCl. And we work out which chemical is the limiting reagent by referring to the equation. And sodium hydroxide and HCl react together in a 1-to-1 ratio to make sodium chloride and water. So since the ratio is 1 HCl reacts with 1 sodium hydroxide, the chemical that has got the smallest number of moles will be the limiting chemical, and the one with the greatest number of moles will be in excess. And now we've decided that this value of 0.02 moles, that is the value of N that we need to use. And so the final step, delta H equals Q divided by N, well, we've got 3.135 kilojoules, and we're dividing it by 0.02 moles, which is going to give us 156.75 moles. And we need to recognise that this is exothermic because the temperature went up, so we need to put that negative symbol in here. And then finally we need to round it to the correct number of decimal points. Now really I've been a little bit careless in my setting out earlier because I've used 2 significant figures and 1 significant figure here, when really you should use 3 significant figures for all the way through, like I've done with the temperature. So let's assume that I've used 3 significant figures all the way through, and so that means that I now need to round my final answer to 3 significant figures as well. And that's the most common number of significant figures in an exam question, but they usually make it clear how many you need to use. I mentioned earlier that I think it's easier to treat the specific heat capacity as being in kilojoules per kilogram per degrees Celsius, and the reason for that is here at the stage where I had my answer for energy change as 3.135 kilojoules. If you had left the masses of the liquids in grams, the calculation would have been really similar. The only difference would have been 50 as the mass instead of 0.05. And so therefore our energy change would have been 3135 joules. And then we would have to have divided that by 1000 to get 3.135 kilojoules. And then we could have plugged the number in down here as before. So the only benefit of dividing by 1000 earlier on is that you don't have to divide by 1000 later at this stage. So as I say, I prefer the step that follows it through down like this, but there's nothing wrong with going to a value in joules and then dividing it by 1000 to have it in kilojoules. The important thing is to divide by 1000 at some point. And to just finish this off, the units are kilojoules per mole, and per mole of what? It's per mole of the limiting factor. So we have determined that the HCl is the limiting factor, so it is minus 157 kilojoules per mole of HCl. The second example to consider is an example where you have some kind of solid. Let's say we've got 2 grams of zinc, and we're going to add it to a liquid, which might be a solution or it might simply be water. On this occasion, I'm going to have this solution as being copper sulfate. And this will be a displacement reaction, but it might not have to be displacement reaction. It could easily be a enthalpy of solution, which is where you're just simply dissolving one solid in another. So we won't actually do the calculation this time, but we'll look at where we'll get our values from. And so if we think about the temperature change, we need to know the temperature of the copper sulfate at the beginning and at the end. So our delta T will come from the copper sulfate. And so our thermometer would of course therefore need to go into the copper sulfate. And that means that therefore the specific heat capacity would be the specific heat capacity of the solution, which once again we would assume it would be the same as the specific heat capacity for water, so 4.18 kilojoules per kilogram per Kelvin. And then in the experiment we would add the zinc to the copper sulfate and we'd stir it probably by stirring with the thermometer. Now in this example, the M for the amount of substance being heated is in fact the mass of the solution. And so M equals 40 cm cubed of the copper sulfate, which is 40 grams, or, as I say more usefully, 0.040 kilograms of copper sulfate. What is not included is the 2 grams of zinc. We are not considered to be raising the temperature of the zinc, only the copper sulfate. And so that's a really important pitfall to avoid. And so for us, Q equals mc delta T, which is 0.40 times by 4.18 times by whatever the delta T is in this example. And then the last thing to say in here is the moles that you would use next would either be the moles of zinc, which you would find by doing mass divided by AR, or the moles of copper sulfate, which you would find by doing concentration multiplied by volume in decimeters cubed. And you would be looking to see whichever one would be the smallest. So 2 divided by 65.4 would be the number of moles of zinc, and 1 multiplied by 40 over 1,000 would be the moles of copper sulfate. And once we've run through these calculations, we can see the 0.031 moles of zinc is the smaller value than the 0.040 moles of copper sulfate. And since the reaction equation is once again a 1-to-1 ratio, zinc plus copper sulfate is going to make zinc sulfate plus copper. In a 1-to-1 ratio, we are literally on this occasion just looking for the smallest number of moles. If it wasn't a 1-to-1 ratio, you would factor in the multipliers in the equation when working out the limiting factor and excess, and it would be a slightly trickier situation. And so this moles of zinc is limiting, and that is what you would use for the N value in the final calculation, that delta H is Q divided by N. And as before, displacement reactions will always in fact be exothermic reactions, and so this value in this case would be negative. I know we don't quite have all the data to run the final calculation, but what I would recommend almost is before you start doing your actual calculations, take a look at what the temperature has done. Okay, temperature has gone up, it's going to be negative. Stick in kilojoules per mole because those will always be the units, and then you can work out the rest thereafter. I've said displacement reactions are always exothermic. Enthalpies of solution, so dissolving something, can be an exothermic reaction, but it can also be endothermic, so there's no easy pattern to remember for that one. And just so we've got a number to work through, let's suppose the temperature change was 20 Kelvin. That will give us a heat energy change of 3.344 kilojoules. And this is our Q, which we would then bring down to the bottom here. And we would divide it by our limiting moles, which was the zinc, which was 0.031. And when we plug that into the equation, we get an answer of minus 107.9 kilojoules per mole. And then when we go to 3 significant figures, it's minus 108 kilojoules per mole. And once again, the per mole, it's the per mole of limiting reagent, which is per mole of zinc. The final example of enthalpy change experiments that you could encounter is for a combustion reaction. Actually from this third example, where we get the origin of the word calorimetry as used to describe these experiments. Now, calorimetry is derived from the Latin word calor, which is for heat. And so calorimetry is literally a way of measuring the heat energy changed in the experiment. And so the setup that we've got shown here is often referred to as a simple calorimeter, and that indicates quite strongly that there are other different types of calorimeter, such as flame calorimeters or bomb calorimeters, that I'm not going to go into in this video, but they definitely exist and you can check them out if you wish. And in an experiment like this, you would have some water with a thermometer in, so we can measure the start temperature. And we would either have this standing on a Bunsen burner, or potentially it would be better if we had it clamped somewhere higher up and then we had a retort stand on here. Either way, what is absolutely essential is that we have some kind of alcohol or a spirit burner underneath the beaker. And what happens is really clear. The alcohol burns and the temperature of the water rises. And so in terms of our calorimetry experiment, if the temperature goes from 20 degrees C up to 70 degrees C, our delta T is 50 degrees C. And so this is the temperature change of the water which is above the spirit burner. C is, for the first time, 100% not an assumption because it is water that we are warming up. And finally, the mass is once again to do with the mass of water. So M is 100 grams because the density of water is 1 gram per cubic centimetre, or more helpfully, as I keep saying, 0.1 kilograms of water. I meant to mention this earlier. Sometimes in the exam question they say slightly confusing seeming phrases such as assume the density is 1 gram per cubic centimetre, and that leads to a really frustrating occurrence of people going, 1g, that means 1 gram, and so they treat the mass, m, as 1 gram, and that's not what this is telling you. This is telling you that you are allowed to assume that 100 cubic centimetres is 1 gram, because it's telling us that this is 1 gram for every cubic centimetre we've got. Since we've got 100 cubic centimetres, this is 100 grams. And so now we've got, in fact, everything that we need for Q equals mc delta T. We've got the mass of the water, we've got the specific heat capacity of the water, and we've got the temperature change of the water. And this seems really weird because we've completely ignored the alcohol altogether here, even though this experiment is likely to be find out the enthalpy of combustion for this alcohol. But now in the second step of these calculations, that's where we need to use the alcohol, because this is where we get our moles from, because it is the moles of alcohol that have been burnt. And we would calculate that value by taking the mass of alcohol that has been burnt and dividing that by the MR of the alcohol, whether it was methanol or ethanol, etc. And then this value for moles is what we would plug in down here, and we'd do 20.9 divided by whatever that number of moles was, and then we'd get our final answer of something. It would be negative because this is exothermic. The temperature would always be going up in a combustion reaction, and it would be something kilojoules per mole. In a school lab, an A-level chemistry energetics experiment, we'll have all the same concepts being explored as we've just been looking at. And if you were looking at combustion, it would most likely look really, really similar to that. But if you were exploring one of the first two types of enthalpy change experiment, it would look quite different. So, first of all, you wouldn't be doing the chemical reaction in a beaker. Instead, you're likely to be placing your chemicals in a polystyrene cup. And we use polystyrene cups because they are good at insulating, because they've got trapped air. So not only will they keep any evolved heat energy inside, they will prevent heat energy from entering the chemicals as well. For the same reason, we will have trapped air between our beaker and the polystyrene cup. And once again, this is a good insulator, and so we're going to be reducing heat loss to the surroundings because we've got trapped air. And then we will put a lid over the top of our polystyrene cup. And the lid will reduce heat loss again, but this time it will reduce heat loss by convection. Convection, if you remember, is the movement of fluids, and on this occasion, and on most occasions really, we're talking about air. And so if heat was generated in this reaction and the temperature went up, the air above the chemicals would get warmer and then they would rise up. And if that lid was not there, they would carry on and they would leave. However, what happens because we've got the lid is the warm air will gradually cool down and it will sink back to the bottom in a mini convection current. So the polystyrene cup insulates because it is full of trapped air and that reduces conduction. We've got the lid that minimises convection, and then last of all, whatever chemicals we're mixing together, they need to be stirred. So there are two solutions to this problem. The first and most likely solution is that you will have a thermometer, and that thermometer will be poked through a hole in the lid, and then that thermometer will double up as a stirrer because you'll be able to stir with the thermometer. Now I'm trying to draw here a digital thermometer. They come in all sorts of varieties, but digital thermometers are often preferred because they allow us to see very quickly what the temperature is, and they also have a maximum minimum function, which is sometimes a nice shortcut for working out the temperature change because you can see what the temperature begins at and you can see what the maximum is that it reaches. An alternative to this would be to have a space for a thermometer and for a stirrer as well, but that, for me, would reduce the insulation properties of the lid by puncturing a second hole into it. So it's definitely preferable to have the thermometer doubling up as the stirrer. And so the thermometer is where you would get your data for delta T. The liquid inside the polystyrene cup, that's where you would get your value for M, and it's also where you get your value for C, because we would assume that whatever the liquids were, it was likely to be the same specific heat capacity as water. Obviously it would vary in terms of the moles depending on what the chemicals were that you were using and their quantities. I think now is a good point to have a refresher about how you would calculate percentage uncertainties for an experiment like this. We'll just look at how you generally calculate percentage uncertainties and then look at two examples. So in general, your percentage error, which is sometimes referred to as your percentage uncertainty, is calculated by taking the uncertainty and dividing it by the thing that you are measuring, the quantity you are measuring, and then multiplying it by 100. And the core concept behind this is that if you have your measuring cylinder here and you think you've got 25 cubic centimetres of, say, hydrochloric acid in the neutralisation experiment, if the uncertainty is plus or minus 1 cubic centimetre, which it's likely to be for a measuring cylinder, what that means is you may, in fact, only have as much as 24 centimetres cubed, or you could have 1 centimetre cubed more, and that would be 26 cubic centimetres. So the percentage error in this case is the uncertainty, which is 1, divided by the measurement, which was 25, multiplied by 100, which gives us an uncertainty of 4%. So that means that we could be 4% higher or we could be 4% lower. Now, in reality, of course, you wouldn't use a measuring cylinder to measure 25 centimetres cubed at A level. You would use a pipette, because pipettes have just got the one graduation on, and once you get to that line, you've got 25 cubic centimetres. And the percentage uncertainty for a pipette is found using what's called the absolute uncertainty of plus or minus 0.05 cubic centimetres. And so, assuming that we've used the same measurement, our percentage error is found by taking this uncertainty, 0.05 cubic centimetres, divided by 25 multiplied by 100, which on this occasion is going to give us 0.2% error. So significantly better to use a measuring cylinder. The final example I want to look at here is for your delta T, because that's specific to this experiment. If you've got a thermometer that's measuring to 1 decimal point, you're likely to be told that the uncertainty with the temperature reading is plus or minus 0.05 degrees Celsius, because it's normally taken to be half of the interval between measurements, or half a scale division. Now delta T is complicated slightly because we're measuring a starting temperature, for instance 20.0 degrees C, and then we're measuring a final temperature, say 45.0 degrees C. Now each of those measurements could be out by this plus or minus 0.05 degrees Celsius. And so when we're working out our uncertainty, if we've got repeated measurements like we have here, we need to add those two together for each of the repeated measurements. And so our actual uncertainty for the fact that we've done two measurements in order to work out what our delta T is plus or minus 0.1 degrees C. So that means that our delta T, in this case, it's easy to see that our delta T is 25.0 degrees C, but we are plus or minus 0.1 degrees C, because in order to arrive at that value of 25, we had to make two measurements, which means that the uncertainty with each individual measurement had to be doubled. And so to calculate our percentage error, we need to take this uncertainty of 0.1, divide it by 25, and then multiply it by 100, which on this occasion is going to give us a percentage error of 0.4%. Once you've done this for all of the percentage error calculations for a whole experiment, you would most commonly add all of those values together to get a maximum percentage error for the whole experiment. For obvious reasons, school experiments are unlikely to hit upon the exact correct answer that you would find in a textbook or online for the enthalpy change for a particular experiment. And the greatest reason for this is that heat energy is lost to the surrounding gases. And if you think about what this means, if you are not catching as much of the heat energy as you maybe should be, this means that the reaction will seem to be less exothermic than in fact it actually should be, which is something to be mindful of. Not only is this the case, if you consider the different types of experiments that we've explored, some of these are going to be more prone to heat loss than others. In general, it's fair to say that the larger the temperature change in an experiment, the greater the heat loss will be. So something like a displacement reaction that only gets warm rather than hot is likely to not lose that much energy to the surroundings, whereas something like combustion, where the temperature might get to boiling point for our water, the heat loss to the surroundings is going to be significant. And also the experimental design is a factor as well, not just how hot it gets. The combustion experiment is probably by far the greatest heat loss to the surroundings, and that's just due to the systematic issues that are involved. So as the flame of the alcohol burner is warming up the water, so too is it warming up the air particles, which will then move away from the flame through convection and be replaced by colder air. And so we've got heat loss through the sides of the beaker that is being heated, and also through the top, and also from the flame. So there is lots of opportunity for heat loss to the surroundings. And this can lead to quite big issues, some of which we can account for, some are harder. The ones that are easiest to account for are for the reactions that take place in the expanded polystyrene cups. Even though they are good insulators, the polystyrene cups will still lose some heat energy from the top and the sides, and we can try and account for this by plotting a cooling curve. And so what you would do in this instance is you would get your timer and you would measure the temperature of your chemicals periodically for the whole duration of the experiment, and crucially, we would keep measuring the temperature after the reaction is over, and we'd be looking to see the rate at which the chemicals cool down or warm up after the experiment has finished. So to do this, we would get ourselves a results table, and we would get ready to plot a graph with the data that we collect. Because my table isn't very big, I'm not going to use any decimal points. So at the beginning, temperature's 18 degrees C. 30 seconds later, it's also 18 degrees C, because we've not done any chemistry yet, we've not done any mixing. After 60 seconds, it's still 18 degrees C. 90 seconds, it's still 18 degrees C. At 120 seconds, so 2 minutes, we don't take a measurement, because this is the point that we're going to mix our chemicals. And then we would wait for the next 30 seconds to pass, and then we'd measure the temperature again, and it's 24. And then we'd measure the temperature 30 seconds later, and it's 29. And then 30 seconds later, it's gone down to 28. and then 30 seconds later it's gone down to 27, and then maybe it goes down to 26, 25, 24, 1 degree C every 30 seconds, and we would keep going on and on and on until the temperature either returned back to what it started at, or until maybe 6 or 7 minutes of cooling had taken place. Then we would take a graph paper and we would plot our graph, and on the y-axis we would have temperature in degrees Celsius, and on the x-axis we would have time in seconds. The mark schemes for graphs always have certain requirements, and the number one is that half of the area that you've been presented with is used to draw the graph. And this means that if this was the area on here, we would need to make sure that we used half of the paper as an absolute minimum. And the way to get around this, first of all, in a temperature against time graph, is to not start at 0. Because if we did that, we would have 18 degrees between our starting temperature and 0, and then we would have what looks like maybe 11 or 12 degrees between our starting temperature and the highest temperature. So we're already guaranteeing we're not going to get the marks here, because we are choosing to not use more than half of the y-axis that we're plotting. So we mustn't start at 0. I'm going to start here at what looks like the origin at 17. There's likely to be another mark for putting time on the x-axis and temperature on the y-axis, although not always the case, because that's pretty obvious in a graph like this. You'd maybe get marks for having a regular scale, but again, I would say that these two are pretty much implied for graphing skills. The next things that you definitely get marks for are plotting your points. So at 0 seconds it was 18 degrees C, and then 30 seconds later it was 18, 18, 18, and then this point here was the 120 second mark, and that's when we didn't measure the temperature. Then the temperature 30 seconds later shot up to 24. I'm not plotting this properly, as you can see. Then it went to 29, and then every 30 seconds it went down 1 degrees C at a time, and I stopped recording in my table, but let's continue it on a little bit. And so the next thing that you're guaranteed to be getting marks for is plotting the points correctly. There is normally a little margin for error, plus or minus half a square for each point. And you're sometimes allowed to make one mistake, but not necessarily. And then the final marks are for plotting best fit lines. We need to draw 2 best fit lines for a graph like this, because there are 2 distinct regions where we can see a trend. And not only do we draw best fit lines, we need to extrapolate those best fit lines to go beyond the range where we have data. To extrapolate means to look at the pattern and work out what would happen if that pattern had continued. So if we look down at the start of this reaction, where the temperature was 18 degrees C, we can be pretty confident that that pattern, we can see that the best fit line is a flat line, and we can also be confident that the best fit line would continue if we hadn't done anything else in our experiment. So you can either continue that with the solid line as before, but often they like the extrapolations to be a dashed line. And you are extrapolating both of your best fit lines at the very least up to the 122nd line, to the point where you didn't measure the temperature. Now the second best fit line that you're going to draw needs to follow the pattern of the cooling. And so looking at this, we have got a quite regular cooling because I've rigged the numbers. And the crucial thing is this best fit line shouldn't be too steep. It needs to pass through as many of the data points as possible without going below too many of the points, and certainly without going below the maximum, because then you'll end up with an extrapolated point that goes to a lower temperature than the one that you recorded. And so the idea here is that we're going to go to a higher temperature than we recorded. So I'll make my best fit line something like this, and then I've already extrapolated it beyond the data, and I think, let me just continue it a little bit further, but I think it's already gone past the 122nd line. And so the final job is to work out what our temperature change actually is. So it was 18 degrees at the beginning, and then it went up to here, and we need to work out what the difference is between these two numbers. And so we can see we don't have any data on the y-axis properly to use, but you can see that my number here is in theory 29, and that we've gone 1 or 2 degrees above that. It's not always going to be that big. This is just a bit of a sketch graph to show you the core concepts, but the idea here is that this would be our maximum temperature that we used, and so the delta T would be the maximum, take away the start temperature, and that's going to be usually to 1 decimal point that you're going to be recording those numbers to. Notice I haven't said anything about connecting the points up. There are no marks for drawing anything in this region to go point to point following the pattern like this. All the marks are derived from allowing us to work out what this delta T is from those two extrapolated best fit lines. And remember, this is for two purposes. Firstly, as I've already said, this process accounts for some of the heat loss that occurs during the reaction. And the second point, which is a bit less obvious, is this accounts for the fact that the chemicals will cool down as they are warming up. And what that means is that not all of the heat energy will be given out in one solid thunk. There we go, here's all the heat energy. What will happen is some will get given out, then the chemicals will begin to lose that heat energy to their surroundings simultaneously as the next amount of energy is being released, and then there'll be some cooling. And so even though there is a net increase in temperature, heat energy is still being given out to the surroundings as more heat energy is being given. And so this, again, extrapolating, accounts for that to an extent. I just wanted to give you two more examples of extrapolating because it isn't an easy concept. So if we take the top one, which is an exothermic reaction again because the temperature goes up, our extrapolating at the start would look something like this. And then the temperature of mixing was not measured, so we need to extrapolate the other line. Again, we need to make sure we pass through the warmest temperature, and if in doubt, go slightly above the warmest temperature. And then we need to look at the difference between these two lines. I don't think I extrapolated that quite far enough, so I'll continue that on a little bit like this, and then we can look at the difference in temperature at that point. And our delta T would be whatever was between those 2 points. We can do this for an endothermic reaction as well. We're just looking for the opposite trend. We're looking for the rate of warming up. The beginning pattern is always easy. It should be a flat line. And then the temperature raise pattern is also easy, because the temperature ought to increase at a reasonably steady rate. And then the bottom line needs to be extrapolated significantly more, actually, to the temperature at mixing, which is something like this, and then the delta T would be there. And just to finish this extrapolation section by saying that the core concept here is that chemical reactions will either warm up or cool down at a consistent rate, so you can work backwards, which is what the extrapolation is, to look at the rate of warming up and what it must have been during the stage when it didn't appear to actually be warming up. And that's the same is true for the cooling down. So let's just sum up those calorimetry key steps for the calculations. First of all, you're going to need to do Q equals mc delta T to work out the heat energy change for this reaction. Then you're going to need to work out the moles of the limiting reagent by doing moles equals mass over mR, or moles is equal to concentration times by volume. And having done that, maybe for both of the reagents, you will know which chemical is now in the limiting factor, and so should be used in the final step, where the enthalpy change is Q divided by N, where N is the moles of the limiting factor. And then finally, the big reminder is to ask yourself, is this exothermic, in which case you need to put that negative sign in front, Is it endothermic, in which case it will need the positive sign. And the easiest way to remember how to do that is to look for the delta T. Has the temperature gone up? Well, it's exothermic and it's negative. And last of all, for your calculation, you need to remember that the units will be in kilojoules per mole. Now that's the standard way of approaching these calculations. There are a couple of different ways that they could get you to use all these relationships in a different order. And so to help you approach that, there is a formula triangle. Not everybody likes formula triangles, but there's a formula triangle for Q equals mc delta T, and it's got Q on the top and the other three terms on the bottom. And so M equals Q divided by C delta T, just as a for instance, because what you do is you cover up the thing that you're looking for, and we're looking for M, so what we're left with is Q divided by C delta T. Covering up C, C equals Q divided by M delta T. And delta T equals Q over MC. And similarly, if we are rearranging Q equals mc delta T, we might be required to rearrange the delta H equals Q over N. And so again, we can have a formula triangle here, which once again, Q is on top. So that's okay. Q is always on top and everything else is always on the bottom of the formula triangles. That's a nice way to remember that. So we will finish off this video by looking at the application of one of those rearranged forms of the Q equals mc delta T expression. So let's look at this question. Calculate the maximum temperature that could be reached, so maximum temperature that could be reached if 200 centimetres cubed of water at 18 degrees C are heated by an ethanol spirit burner. Now we'd be given some more information to help us answer this. And so let's follow up with some more information. The enthalpy of combustion of ethanol is minus 1370 kilojoules per mole, and the mass of the spirit burner at the beginning was 3.240 grams, and then at the end it was 30.24 grams. So it's decreased a little bit. So now let's have a reread of that question. We've been asked to calculate the maximum temperature. So what that is a final T. So what temperature did it get to? We know that we're heating 200 grams of water. So let's quickly sketch the apparatus. There's our water. We've got 200 grams of it, and it is starting at 18 degrees Celsius. It's being heated by a spirit burner, and at the beginning it's got a mass of 32.40 and it goes down to 30.24 grams. And the specific heat capacity of the water, we aren't told necessarily, but we probably would be told that C is equal to 4.18. And we're also told that the enthalpy of combustion of ethanol is minus 1370. So I've just reordered the information that we've been presented with in a diagram form that makes it a lot easier for me. Now, the most common error in this situation would be to refer to the enthalpy of combustion as Q, because it's got kilojoules in it, but this is kilojoules per mole, which tells us it is an enthalpy change. And so, since our final task is to work out a temperature, that tells us that the task just before that will be to work out what our temperature change is, delta T. And so this requires us to rearrange the Q equals mc delta T expression to delta T is Q divided by mc. Now we have already got the M, 200 grams, so 0.2 kg, and we know that C is 4.18. So that means that the previous task must be to work out what Q is. Now Q is, in the delta H is Q over N expression, Q is delta H multiplied by N. We've been given delta H minus 1370, so that means that the task prior to this will be to work out the mass of ethanol being burnt, which is mass divided by MR, which means that our very first task is to work out the mass of ethanol that has been burnt. So let's do that now. 32.40 was the starting mass. It went down to 30.24, so we need to subtract that, and that gives us a mass of 2.16 grams of ethanol being burnt. Then the MR of ethanol which is CH3, CH2, OH, is 46. And so moles equals mass, 2.16, divided by MR, which is 46, which gives us an answer of 0.0470 moles to 3 significant figures. Now we know our moles, we've got to multiply the enthalpy change, which is minus 1370, by the number of moles, which is 0.0470, and that gives us an answer of 64.39 kilojoules. Now we can ditch the negative sign here because energy is a scalar quantity and we don't need that negative sign at all. Then the delta T is Q, 64.39, divided by MC, so 0.2 times by 4.18, and that gives us a delta T of 77.0 degrees C. Then the final job is to work out what that final temperature is. It starts at 18 degrees C, the temperature is going up, we know that because of the type of experiment it is, and because the enthalpy change is negative, so that means the temperature will be going up. And so to work out what our final temperature is, we need to get our starting temperature 18 and add 77 to it, which gives us 95.0 degrees C as our final temperature. And so you can see that we're using the same relationships, Q equals MC delta T, delta H equals Q over N, but we're rearranging them and applying them in a different sequence. Okay, that's the end of this second and final video about Year 1 energetics. I hope it's been useful. We'll see you again soon for another A-level chemistry video. Bye-bye.